this year here at ETH, and Professor Smith gave me the privilege of being able to tell you some of the things that we've been working on that have to do with the modeling of urban systems with an eye on future systems. So some more background. Myself, I'm not only a professor in the United States, and I'm from computer science, so not actually an architect, but I am able to speak with architects and they somewhat understand me, so hopefully you'll be able to understand as well. And the particular project we've been working on is in mixing computer science with architectural design. Of course, a perfect fit here to the chair of information architecture. So let me begin. So brief kind of introduction, motivations. Some of this will be obvious in this context, but I want to kind of build up towards later things. So you might have, if you come very much from an architecture background, then maybe you focus on buildings. In our work, we kind of work on several scales. We think about buildings, we think about neighborhoods, we think about cities. So in general, I'm going to say cities, but we kind of mean this whole gamma going from buildings to cities. So first, urban areas are primary centers of social, economical, and educational activities. Clearly, we know this, right? Cities are the thing we live in. They're very important. Some interesting numbers. Urbanization, the process of cities growing and maybe people even moving to cities is only increasing. Roughly speaking, in the year 1900, 14% of the world lived in cities. And that was almost 1.6 billion or 1,600 million, depending which system you use, people lived in cities. Today, more than 50% live in cities. There's more people, but a higher percentage. In the future, it's only believed this will increase even more. And you can Google around and find different predictions, but this process of urbanization is only increasing. That means you guys will have a secure future in jobs, right? Because people need to make good buildings and good cities. So you're in the right field. Of course, this is a very unbiased opinion. So a few pictures. So why model urban areas? Why do all this? Of course, computer science answer. Entertainment is one, right? You model cities so that you can have games, you can do movies. Right, Procedural is a company that's actually, I'm sure you heard about it, right? That's based here in Switzerland. So designing these for entertainment is useful. People also care about urban models for things like visualizing the past here, right? Cities, Pompeii, and so forth. Also, Google Maps and other navigation systems require also some type of urban model. Maybe it's 2D, but some parts is even 3D, like you have Street View, and you want to go around and recognize where are you and where should I turn left and where's that store. It'd be great if you could have an instantaneous 3D model of that part of the city. And so that's maps and navigation. And then urban planning, of course, very relevant to what's done in architecture and in urban design and urban planning itself, is you want to create master plans of future cities so that you can create them with some particular objectives. In this case, energy conservation, well, currently what's in style, right, is sustainability, reducing energy, reducing emissions, and so forth. Okay. So what's a problem statement? Well, first, modeling buildings is hard, right? You guys, if you're an architect, this is what you do. This is hard, right? It's not a trivial thing to model a building in the way that you want it. Modeling the interaction between several buildings, call this a neighborhood, is even harder, right? One building does this, another building does that, and based on the spacing between them, there is a canyon of wind that's produced, and that wind is good or is bad, right? There could be absorption of heat between buildings, and then of course there's even the open spaces and things like that between buildings. Okay, so it's even harder with multiple buildings. And when you have an entire city, it's even more difficult, right? The problems are even more complicated. So therefore, modeling your cities, I'm going to say, is almost unmanageable, right? And so this is kind of the gamma of things. All right, so it's a hard task in general to model and to understand what's happening from building to city scale. All right, so a interesting side note. There is a well-known scientist from the United States from the 1950s. His name is Warren Weaver, and he gave an interesting kind of summary of science. And kind of put in perspective some of these problems. Let me tell you some about this. This paper appeared in a journal in the 1950s, and Warren, Dr. Weaver, divided all of problems of science into three major categories. And I think this is a really illustrative or informative subdivision. The first is what he calls problems of simplicity. This means it's a problem which you can model with a little equation, with E equals mc squared, little but important equation, F equals ma, and other things like that. Right? These are equations which are simple. Maybe differential equations in more modern terms, and then you have things like thermodynamics. Right? These you can actually capture with an equation very succinctly. Next group of problems is problems of disorganized complexity. These are problems which are very large and complicated, and it's disorganized. There is no simple equation that's governing what's happening. In fact, it's so disorganized that you can't really even think these equations exist, some way of understanding it. So for instance, problems at the atomic level. You have atoms moving around, and you have electrons, and you don't know exactly what the electrons and so forth are doing. You only have statistical models kind of capturing more or less what's happening at that level. So the problem of disorganized complexity. And then there's a third category, which are problems of organized complexity. Here, the problems are really, really complicated. There's many factors, but there is actually a logic. There is an organization. It might be non-trivial, but it actually is sensical. And so cities are an instance of this third category, as well as several other biological beings, biological structures, being entities, right? So if we can find ways to model buildings, the interaction of buildings, the interaction of cities, we're actually solving problems which are really, really large and complicated, and that methodology could actually help people because they live in cities and science in general. So addressing these problems of modeling cities and buildings and so forth is a big challenge, and whatever methodology we learn is going to be useful for other things as well. Okay, so a few other characteristics. The modeling of future cities is a multidisciplinary task, right? So it means that the city has social sides, economical aspects, meteorological, architectural, engineering, political aspects, and so forth. All these things have to be considered when you're modeling buildings, neighborhoods, and cities. And the next, there's multi-scaleness, right? So I've already kind of repeated this, right? When you go from small-scale building efforts to regional scale or city scale of hundreds of square kilometers, right? This is a large range of the spectrum. And this is inherently part of the modeling of future cities. We have to also consider this aspect. The last one is multinational. So the idea of modeling future cities is of concern to one nation and to many nations. And in fact, this can have interesting ramifications to the problem, right? You come up with a methodology that works in one city or region, right? Does the same thing work in another city? Not. Another aspect is what we do in this area affects what happens over here, particularly when they go to global issues like, the potential global warming, consumption of energy and resources and waste and so forth. These affect perhaps multiple countries. And I guess also there's governmental involvement in that way, right? One nation, another nation might have to talk about how they agree when they have agreements as to hybrid cars and reduction of energy. Sometimes there's treaties amongst countries and so forth. So these are all issues that we have to be thought about. So it's also a multinational issue. So just to get maybe some feedback, maybe have some inspiration, this is a question to you guys, what are problems caused by this multidisciplinary nature of the problem? The fact that modeling, building, cities, and so forth requires multiple disciplines. What are some problems you think arise from this being kind of a fundamental fact?
Communication between disciplines.
Communication, right, that's a clear one. What type of particular?
Scientific maybe, or specific from each subject when they come together so that they understand each other. Maybe graphically or...
Right, so form of communication, right? Some things might be graphical, other people might be, not verbose, but verbal, right? They want to talk with words, and they have politics and rules, right? And science people sometimes have, equations and numbers, and maybe politicians have to think about policies and guidelines, and, how do you merge that? And that's a very, very challenging problem. In fact, this room is part of an effort to try and provide a common way of doing that, a prototype of a common way of doing it. Any other problems you could think of? Anybody here is not in only to study architecture? That would help. Anybody have a hobby? Something you do outside of work, school? A life outside of ETH? No? So even inside a city, there is concerns for different people that are aware to different types of people, right? You might be a gardener, so you care about gardening, and that gives you a particular set of concerns, and the multidisciplinary nature. One is the communication barrier, but the other is what you want, what you see, right? If I'm a person who deals with vegetation, then for me everything has to do with vegetation. If I'm a civil engineer, then I care about structures and maybe earthquakes and things like that, and rain. So your objectives are different. So not only is your communication language different, but also your objective, what you think about, is different. So your mentality is different.
It has a pretty big overlaps between those two fields, right? I mean, the communication is different because your goals are different, so you think with another perspectives.
Yes, but it could be that, for instance, a politician wants to reduce energy, right? And an engineer wants to reduce energy, but for different reasons.
Yeah, okay.
Yeah?
Yeah.
All right, next. What are problems caused by the multiple scales of this problem? The fact that you have buildings, neighborhoods, and city scale problems. Anybody?
The control over the quality of the project.
Quality. Wow, that's a good one. Yeah, so the quality problem exists at all scales. So what would be the difference?
The level of detail.
The level of detail. Okay, I mean, this is good. So I'll be critical and say if your quality is, 0 to 100%, everybody wants 90% or more, right?
Yeah.
So
If you work on a too detailed scale already your big scale is too detailed, then you don't leave enough space for people who work on other scales to detail it, because they maybe can do it even better on their scale because they're...
So if the top-down people impose strict rules, then but the projects at the building scale you're saying are too restricted.
Or just the other way around, that they're so loose that the projects on the smaller scales actually don't have the correlation that they're supposed to have on a bigger scale.
So then coordinate. They don't develop. So an issue here, I mean, this is all good. I would say a variation of maybe this topic of quality is what can you control, right? So you can impose a building code. Maybe you can impose a overall city level very loose code. There should be so many percentage parks in the city. Of the amount of city should be, 30% park to be a really very green area, something like that, right? But these have to be thought very carefully, right? Like you have to design them to know they're going to be abused, right? So a building code, you make these minimums, which you believe the people who make buildings won't yell at you too much and they will obey, right? And then at the city level, you have to do the same thing, but the specificity is very different. I'm not sure where you have to be more detailed or not detailed, right? If you think of the clever real estate developer, they're going to want to maximize money, which means minimize costs and minimize cost to build something, but maximize how they can advertise it, things they can claim, right? So there are these lots of different details and intricacies of how specific you can be. So it's not clear to me that you can be more specific at the building level, at the top level. It's just very difficult to exactly know that. So this is good. Anybody else have any other people? Yes?
Human scale, I get a feeling from the city plans, they always plan buildings for the numbers of people, but when it comes to design, it remains within the boxes with the number of people, and they forget to design the architecture also into the human scale so that the people don't run away.
Okay, that's right. The human scale, yeah. So maybe that's the human dimension, right? There is spatial scale, but other dimensions, right? Not that we just call this. I don't know what the human scale would be here. It would be one side is friendly to humans and the other side is not friendly. Is that the scale? So maybe.
Somehow, yeah, if something is too big or if it's planned for such, I don't know, very, very well for this number of people, this space and this amount of air, but if it doesn't remain in human proportions or it's too big,
Okay.
It doesn't work. So.
Okay. Yes, that's a good example. There are other scales, and they also have different dimensions, or maybe it's vice versa, different dimension with different scales.
I think that has a lot to do with the fact that both problems are integrated, so different people work on different skills, and therefore the communication between the skills and people is
Yes.
more sparse.
Right. So all these combined. It's good. It's good. And what are problems caused by this multinational aspect, multinational interest?
Cultures.
Cultures? Yes. So, I've recently been to Qatar a few times. I was really intrigued by all their quick growth. They're like the Arabic area, but they're kind of a newer one, and the latest ones that are growing. And you go there and you see there's so many different things that they need solutions for that are completely different to what's needed here. Yet you want to all publish papers and do the same thing, kind of, right? You all want to reduce energy consumption, water, and other things, for instance. But they just is different worlds, right? So it's hard for everybody to maybe have the same priorities, right? Even if you as a group of countries form the next, that G something group, right? And you all want to reduce energy. There's just different things that are pro and con. You go to, for instance, Arabia, right, and other places, oil is cheap, right? So yes, you argue you should reduce the consumption, but they say it's so cheap, right? And then the dynamics of the people, the mentalities are different. You go over some other country like Europe and so forth, oil is expensive, gasoline is expensive, so you're easier to convince some other things. And how do you deal with that? Any other people have other ideas? Okay, so just some ideas of problems and with your suggestions about why the modeling of cities is difficult because of the multidisciplinary, multi-scale, and multinational issues. Alrighty, so now let me kind of try and organize the world that myself and other people like me work with. Look at the time. Okay, so there's many ways to organize this idea of modeling, simulating, and visualizing spaces going from buildings to cities. Here's one way. We first begin with a geometrical model. We make some structure. And this structure, we design and we model it in a very general sense. Then we do a behavioral simulation for some behavior. If we're a civil engineer, maybe we care about resistance to earthquakes. If we are some city psychologist, right, then we care about the perception of the city, the open space, and things like that. And then we visualize, which means we look at the results in some visual way because we're humans, we see stuff. So this is a very generic pipeline. And as I mentioned, there's multiple ways we can model the geometry, multiple behaviors, and multiple ways we can visualize. So a problem with this pipeline. An accurate geometrical and behavioral model is crucial. Clearly we need to do this and do that very well. Otherwise, what we see at the end is not very useful. A geometrical model, which is something a little more what I focus on, is needed. A different one is needed maybe for each behavior. And these are difficult to obtain. So a question, how do we obtain geometrical and or behavioral models of buildings, neighborhoods, and cities? I mean, it might be some straightforward answers to this. So you can, if you have any answers, tell me. The straightforward ones are obvious, but if you tell me non-obvious ones, that would be even better. How do you make a model? So what's a model? A model could mean geometry, 3D, AutoCAD, whatever your favorite tool is. AutoCAD's probably out of date now, right? But whatever your current favorite tool is, or behavior modeling. How do you make these models? Anybody? Well, I'll give the first answer. You take out your favorite 3D modeling program, you sit down with a mouse, and you make a model of a building. Okay, next. Any other ways?
You look at a problem and you try to design a model that specifically solves that problem and maybe combine it with another model which will eventually give you an optimized building model.
Okay, so you're saying you are going to use your laptop with your favorite 3D modeling program, and then you're going to go off the side, you're going to bang your head, think a little bit, and go back to the mouse, and you can design.
Maybe not even a 3D model that you're talking about. Maybe you're just first looking at, well, I don't know, numbers, and you see a certain amount of people that have a certain problem, and you just think of functions in buildings that can solve that problem, how to combine these functions, how to, well.
Okay, so you don't necessarily want a structure, you want a graph of functionality and things you want to enable. You kind of want to set the functionality the building should have and the city should have, and maybe you assign priorities and percentages.
And maybe organize it as well.
Organize it, make a hierarchy of some sort.
Yeah.
Grouping. Okay, yeah, that's very information-based. That's a very CS answer. That's in style. Thank you. Anybody else? The ingenious here. Anybody use Lego? I have a 5-year-old. We use Lego every day, and Lego is great. Anybody else? You raise your hand, or you use Lego? All right, good. Anybody else use Lego? All righty. Go Lego, yes. So how are we related to white shirt guy? What's your name? Sorry.
Enzo.
Enzo?
Enzo.
Group of people get together. It's another way you can model things, right? You don't actually need to even have a computer. You can have people come together and organize. Very similar to this, a different way of creating a model is participatory workshops and things like that, right? You don't have to always be thinking about 3D models. Anyway, so there's a variety of ways. And if you had come up with a really cool way of doing some of this, please do email me in private, right? And we'll go and do something. So this is a hard task. But I'm going to propose to you one way of doing it that's, I thought, kind of interesting. Something called inverse city modeling. It's not exactly the best of names, but it's really inverse modeling. So some background. So this is a paradoxical paradigm. So what does that mean? You can read this sentence. We know what we want, but not how to obtain it. Right? So that's kind of the crux of what you can easily say. You know what you want, but you don't know how to get there. Right? Usually as a student, you know what you want. You want an A, you want a PhD, you want whatever, but how do you get there? That's the whole task, right? So same thing goes with a building. So in fact, we can impose an approximate model, right? We can make something with Lego and have the moving parts, right? Or have the structure more or less that we want, but it's not clear how to make this behave the way we want it to behave. So we know a building has floors and windows and doors, or cities has streets, buildings, and parks, and roughly we know how to do it, but we don't know how to make it behave the way we want. But we know what we want at the end. So are there some examples or methodology you can think of? This is a question to you guys of how you can make an approximate model and make it where you making it behave as you would like is not obvious, but so examples of this inverse model, not necessary to do with buildings and cities. I have one, I think, the obvious one in mind, yes.
The game I played 10 years ago, SimCity. You model the city, and then if you model it well, the inhabitants would live there.
Okay, so SimCity is a good idea. It's not exactly inverse because actually it simulates forward. So you try to control, but this is very good suggestion. You have the parts of the city you want to set up, and then you can press this button called simulate, right? And then things happen. If they don't quite happen, well, you know, it's a computer. You press undo, you change stuff. Okay, this is very good. It's getting towards it. Any other ideas? It's a great one.
Isn't it like always like that with games and even sports? Do you have a goal you want to achieve?
Yeah, so strategy, you know, when you play soccer, right, you got to put the ball in that goal over there, and then you got to figure out how to make it. That's true. Another one I have in mind is, you know, reverse engineering, right? Maybe you have some kind of an integrated circuit, a chip, and you don't know exactly what it does, right? And so you want to figure out what it does. You just put inputs, you read the outputs, and you do this exhaustively, and you figure out, oh, this is what it does, right? Other people, of course, try to figure out how it does what it does and do a similar strategy. So this type of methodology is around, right? So in general, it's let's define the output and find the input that yields the desired output. So in this context of this loop here, one way we can describe this is to say, let's go backwards along these arrows. Let's go from the behavior to the geometry. It's kind of like the SimCity example that you mentioned, right? And let's go from the visual content to the geometry. This is actually a little more straightforward, more well known. This field is called computer vision, computer graphics. So they take something visual and try and figure out the underlying model, right? But this here is a little less obvious. Things now to do with like a social networking, Facebook and Twitter and all these things. They try to get from social information and behaviors of masses of people some idea of, you know, the structure of them. Not necessarily mean you can dream about from your Facebook network. You can figure out the physical shape of every person participating. That's kind of hard, right? But that's kind of the idea. You can know what their patterns are, maybe geometrically. So if you add this loop, which is this arrow scheme, which is very easy to make, this means from the known model you create a picture of it. That's very straightforward. You've kind of completed this loop. So the work we've been doing is along these lines, going from behavior to geometry and from visual content to geometry. So let me give you some examples of this in the time that's left to give you some inspiration as one way in which you can model future urban systems that myself and other people have been working on. I'm going to start kind of going some examples here and then some examples from that side. The first one we're going to call inverse 2D procedural modeling. So procedural modeling is a word which means you want to capture succinctly with a couple of text rules, simple things you can write, the process in which something is created. So that's a procedural model. So inverse procedural modeling with only the 2D sense is saying we have the output, you want to find out the rules, the text, the few set of things you should do that produce that output. So here's an example. We start with some lines that seem like a tree, and we have actually, you know, vectors of, you know, 2D curves here. So that's the input to some computer system. Then a computer system figures out, kind of like by thinking really, really hard, analysis, and then creates a type of procedural system called an L system, which is for Lindenmayer system, but some way of writing down rules. And it figures out that these rules, which is kind of saying this symbol gets replaced by this symbol and some other things are occurring. I won't really go into too much detail, but this very simple piece of text is a symbol, kind of like a programming example of this compact programming language. It's only this big, and it creates this. So you get that same output. And the computer determined this automatically. From the picture, found out this set of rules that create this output. So then big, you can do this. What's the advantage? Well, now you have a very succinct way of creating this output. So we can change little things in here, and we can create different trees. These are all trees that are produced by having inverted the procedure to create this one tree. So these are going to be trees that are similar in style and spirit, right? But you have no initial knowledge of how this actually was created. You made up this rule that seems to work. So these are all trees possible from this one single procedure by changing this in some way. So this is some work that colleagues of mine did and I helped with as well. So, okay, that was 2D. Let's kind of go to 3D and let's focus on buildings, to give you an example, right? So here we discovered there is this one rule that's capable of capturing the structure of what's called Manhattan World buildings. So Manhattan World building is a building which, in Manhattan, kind of, it means it's formed only of, the exterior of it is formed only of planes in one of three directions, right? This way, that way, and that way. Not necessarily all buildings in Manhattan or in the world representable by those three planes, but, to some approximation. So therefore, it turns out that to make any Manhattan World building, there is only three possible editing changes you can do as your building grows from the bottom to the top of the top floor, right? Clearly the building could be a box, in which case it's very simple, but normally you want to have a little bit of something happening in your building, right, for some reason. So there's only three possible changes you can do from one floor to the next, and each change occurs 0 or more times. So we have some grammars, and anyway, we come up with this one parameterized rule, piece of text that has some parameters A, B, C, that makes it possible. So then we have a process of how we start with at least 2 pictures of any building in the world. Thanks to Google Maps, we have the pictures, we have the parcel of land at the bottom, and so forth. And then we do a process called color segmentation. We group similar colors. We get these color segments. We put some random guess of number of floors. It doesn't really matter. It's only in kind of a conceptual thing called floor. And then we go from the bottom to the top of this building, and we kind of adapt this geometry of every floor until we kind of make an envelope around this observed building, and we get things like this, right? And then we project the picture back on top if we want, and we get something like that. So this is an example of an inverse procedural building where we figured out how to use this rule over this building. And the pro is it's fast and it's automatic, right? Just give it the picture, you say press button, boom, you get yourself this model. It's not extremely complicated, right? But it's fast, it's automatic, and so forth. So of course, Google gave us money, maybe it will appear sometime near you at some point in the future, next time you make buildings using Google Building Maker. So this is an example of an inverse procedural method for buildings. And then a bunch of other examples. The buildings don't need to be perfectly Manhattan-like, but, similar. All right, so how about another example? So this is actually switching from the right-hand side of that diagram I showed you before. We're going from visual content to geometry. Now we're switching to going from behavior to geometry. So this has something to do with the SimCity example that was mentioned before by person next to Ansel. What is that? Katasha? Sorry.
Katrina.
Katrina?
Yeah, great.
Okay, I'm sorry. Person next to other person. Ansel. Okay. So here in this inverse city modeling, the idea is to tightly integrate behavioral and geometrical simulation to produce a new geometry model, a new city model. So think of it as we have some way, this is stemming from people in urban planning and design, they make urban simulations. I guess SimCity is the game version of something like this, right? Where you have real estate market, you have jobs, population, accessibility, you have a terrain, so you can simulate people in urban planning. This is actually this is how they make a living. This is what they do. They make urban simulators to predict, population, jobs, economy, real estate price. Would be great if you could predict real estate prices, because then you would know where to invest, what to buy, and so forth, right? So these people do this, right? So we took some version of this together with them that was, fair approximation, and then we have an organization of a city which we understand a little bit more, right? We know we have buildings and parcels and roads, arterials and highways. So this is a summary kind of the underlying behavioral geometrical simulation. There are some interactions. This is an agent-based simulation with a bunch of equations and algorithms that implement all of this, right? And this is working in a very tight loop using geometry or using simulations. So what's the visual output of this is the following. This is a top-down view of some city from Google Maps, some city in California, Pasadena, California, kind of an isolated peninsula. And you can see the city top-down. And then we add to this only knowledge of well, this is it's not, plus is somewhat misleading. It actually means that this is the we want to create, but we're going to say we only know the terrain, how high is the ground, the population distribution based on census data, where the highway is, which is Yellow Road, where is the single click of downtown, and then where are the major parks. There's two of them, click, click. And then we produce this output over here. This output is a synthetic model produced by our system, which approximates this over here. This, though, is a picture top-down. There is no geometry information. This is a full 3D model where everything is known, right? You could actually zoom in and you have roads and houses and buildings and so forth, and you have all the 3D information you want. But this is not a perfect copy of this. However, it's quite similar. If we zoom in to corresponding areas, like blue with blue and orange with orange, they are similar. So what does this mean? It means if I live in this city, right, here, that's my house, for real. My house, I really have it there, right? I don't really, but imagine I did, right? Then over here, my exact house is not going to be there. But a house inhabited by the same number of people, in an area of people with the same income, with the same size houses, and approximately the same industry sector of employment will live there. That's what we'll produce. So I'm not going to produce a perfect copy of reality, but something that is statistically similar in a sense. And if I live here in this house in a park, there'll be some houses near park areas in that same place in the city. So this is useful, right? It's not going to solve your 3D navigation problem of being able to then, take your smartphone and use this to, have a street walkthrough of some place that you're actually going to drive, right? But you get approximate information, and it's going to be useful for a variety of applications. So one application of this, for instance, is an urban weather application. Here, we use the same type of input, population based on census data, terrain, and a very classification of what land is used for in some very coarse categories. And then using this same system, we infer the model. This is actually Indianapolis, which is a city near where normally a professor could do university, some big city, about 1 million people, and actually is roughly similar to the actual Indianapolis, and there is some level of detail of the geometry. And then using this, we can then say, okay, let's take this land use data, and with the mouse, we're going to click where we want to make trees appear, because we're going to play. I want to add trees. In fact, this was done in the context of greening of a city. So we want to make this be a green area. Then we use the same tool. We say, same total population, same economy, same real estate price. What would the city look like? So this is a modified version of the initial city. Okay? But it has greening in this corner. So we're not going to say, of course, get rid of 25% of the buildings and the people, because that obviously would give you more space. We're going to tell you how should you move people around so they can keep the same number of people, same job, same real estate market, and so forth. And this is a potential answer. And then we do a weather simulation for some 3-day period that's been calibrated. We know what actually happened and so forth. And then we get a difference of temperature. So this has to do with urban heat islands and other things where people know that in the city, the local weather is affected by your albedos, your building shapes, your building densities, and things like that. So there's this whole simulation that I've now talked about that's going underneath. And as a result of this change, this greening, turns out that the area, so this is the whole state, the whole region. This here is that one city. This is the zoom in. In the zoom in, you can see that on top of the trees, things got cooler. That makes sense. People know that occurs. Over the city, it actually got warmer. So by making the greening here, we in fact made the city warmer by about 1 degree. And rainfall and humidity did some other changes as well. And since, it's a tool, we can just do this like this. We say, let's green this corner, or let's green that corner. Repeat the whole simulation, and we get a hot city, we get a cool city, right? What's your objective? I don't know. Maybe you want to make your city warmer, cooler. Maybe if you're, again, in Arabia, you want to make your city cooler, right? Maybe if you're in South Pole, you want to make it warmer, right? And so forth. You can do circular greening, or you can do some kind of a statistical distribution of parks that there must be so many parks with no more than so more distance between them. So this is a randomly generated set of parks, right? In this case, we get maybe a dry city is what we mostly observe, and here we kind of get a warm and humid city, right? So this is a tool. You can play with how you want to organize your city, and this all works interactively. The last project we call this Urban Vision. And this is a project between University of California, Berkeley, and Purdue ourselves. Here, in summary, we want to develop an open source or a software extension to some urban simulation platform called Urban Sim. Urban Sim was developed by Berkeley. Paul Waddell, who's the collaborator from Berkeley, so this is his tool from the past. And we're going to include a lot of the research we've done, some of it which I've shown you, about modeling of inverse modeling, about actually weather, about urban ecosystems, tree modeling, and so forth. So roughly speaking, the area that this software tool is to be deployed to is a very high-profile area, so we're very excited about this. San Francisco Bay Area, that's also called Silicon Valley. It's where all these technology companies come from. It has about 7 million people and 1.5 million parcels, so maybe 1.5 million buildings, roughly. And we're supposed to deploy it by yesterday, and it seems like we're more or less on schedule. There's a bunch of people, Paul Waddell, myself, another professor, about 10 students, people from MTC. And it has a bunch of components. We have terrains and procedural buildings, landmark buildings. We have simulations of sky, moving pedestrians, moving vehicles, and you have all the underlying urban simulation. You can edit, potential policy changes to your city, how you want to, what rules you want to enforce about future developments, having setback and maximum floor area ratio and densities and where parks should be and so forth, and you can visualize many things. So we did it as a predecessor for now. We do a building typology. We go around, we find out some class of buildings, we create the procedural models that approximate these buildings that are there today, right? And then we can put this into this simulation output and predict the future, how San Francisco will look like after some policy changes, and get this type of output. So it's all interactive program. It's a server client. There's this big effort with many people and so forth. Though recreating reality is not an objective, just to show you how far we can get by only understanding the behavior and the very coarse geometry and then kind of putting it all together, like the example I showed you from that peninsula over California, where we're recreating some part, right? Here is actually a Google view, and this is our view. So there is high similarity. That's what I'm trying to show you here. But this here is a full 3D model. We know everything. We can zoom in whatever you want. That's just a picture. The buildings, of course, some of these buildings, like the Transamerica Pyramid here, look identical because, in fact, we read whatever buildings are in Google Earth and stick them in here. And what's not there, we create ourselves automatically based on the behavioral geometrical information. So here these are pictures of buildings. Right? Here, this is actually a 3D model that's been rendered to create this picture. There's an important difference there. And here are other views, also comparing. Here's another one. So here you can obviously see the Google SketchUp has enabled people to create a few building models, right? We filled in with more, and we added in trees based on some plausible simulation of an ecosystem. But the buildings are not exactly the same, but they have the same properties in the same way that I described previously. Here's a top-down view, and that's it with that. Okay, so I'm trying to stay on time here. So let me end quickly. So I showed you several examples of such inverse modeling ideas. One way we can address the difficulties with modeling of future cities, right? I mentioned at the beginning that it was multidisciplinary, multi-scale, multinational, a lot of coordination. So one way, so logically me and other people are following, is let's define the output and then have the computer help us figure out the most plausible input to cause that output. And that framework has helped us make significant strides forward. So inverse modeling is very promising, but there is still much to do. urban design, modeling, and planning is only growing in importance due to the explained urbanization. So your jobs hopefully will be secure and you'll be high demand. So if you do a good job, everybody will want you. And many cities worldwide are increasingly interested in these design and simulation tools and softwares. Future challenges, just list them quickly. So what is in store for future buildings and cities, right? This is very much the concrete level of things you might be working on with courses in your educational program. Suggestions, so I was going to ask you, but I'm out of time, I'm just going to write down the questions. What are ways in which you can handle design and structural issues, coordinating things that you want? So this is pretty straightforward. I mean, you know how you you have your design, then you have to worry about, is the building going to collapse if I actually do that? These are things that are very concrete that I'm sure you guys can think of and are able to solve and will be solving in the next few years. But an even more difficult question is, how do you do all of the above, but also factoring social, economical, political, scientific, and all these geometric issues, right? How do you factor in this when you're building your future, when you're constructing your future building or your future city or your future neighborhood, right? These are things that are important to consider, and blending them in is very hard. So finally, here's a website from our group. If you're interested in more things, you can go there and go to the Urban Project and you can read about that. Otherwise, I'm done. Any questions? If not, thank you. Questions, comments, suggestions?
I have a question.
Yes.
What does it mean, minus 20 millimeters in the rain?
Minus 120?
Minus 20 millimeters.
Oh, okay. So there, in that weather simulation, the baseline was an actual 3-day weather storm over the city. So by making this city change, there was minus 20. There was less rain than there was. So that same storm was modeled and simulated, applied to the changed city, and the observed issue was less rainfall.
It was
compared to the actual city in some 3-day period that was recorded what occurred.
Okay, question.
Yes.
Isn't it almost impossible to simulate the softer sciences like social, economic, the kind of sciences in the city with just number models and 3D models? Isn't that?
So impossible. I would say impossible is not the right word. I would say hard is the right word.
Yeah.
Right? There is a word is kind of growing, computational social science, right? Computing social sciences. And that is growing, and it is around, and as I mentioned, Facebook and Twitter and all those social networks, they're trying to understand that. That is an instance of computing the social science side. A city also has a social side that's obviously very important and strong. Urban simulation people are trying to incorporate that into their simulation. So maybe it's much more known, concrete, to model concrete for earthquakes, right? But it's, how do you make a city disaster-proof in the social sense? That's more difficult. So I think that's a current desire that people are only kind of having partial solutions to. And so my prediction would be that gives some more time, and that will be more understood. Will there be a closed form equation? Maybe not. And that's why I mentioned this problem of organized complexity. Cities are never going to be a problem of simplicity, which means there's going to be an equation equals city equals building times neighborhood plus 5, right? But there is some organization. It's not at random.
So will always be an integrated discipline of design and computer models.
Well, I mean, there will be a social and a science and a side, right?
Yeah.
Combined, right? Now, yes, people are not robots, so we do odd things, right? And that's okay. Models in a very glorified global sense can account for that, right? And stock market, you can't predict it because it's based on humans and their, their itchy finger, buy, sell, right? But yet people try to predict the stock market, and they do a terrible job, but they hope to improve it, right? In cities, there may be some design choices which are now obvious that you should or should not do. In the past, it was not. So hopefully we'll keep improving that. All right, thank you.